This problem is about finding steam economy of double effect evaporator. Let us read the problem statement. An aqueous suspension at 60 degrees Celsius is fed to the first effect of a double effect forward feed evaporator with a mass flow rate of 1.25 kg per second. The sum of the rates of water evaporated from the first and second effects is 1.0 kg per second. Temperatures of the exit streams from the first and second effects are 100 degrees Celsius and 60 degrees Celsius respectively. Consider the specific heat of aqueous suspension and the latent heat of phase change for water to be 4 kJ per kg Kelvin and 2200 kJ per kg respectively over this temperature range. The steam economy in kg per kg is how much? Let us represent the problem schematically. So we have a feed which is entering at 60 degrees Celsius, which is a aqueous suspension, which is sent to the first effect of a double effect forward feed evaporator. So what is the meaning of forward feed evaporator? Normally the steam is sent to the first effect. If the feed is also sent to the first effect and flow is happening parallelly, which means then it is a forward feed evaporator. Whereas in backward feed evaporator, feed will be introduced in the last effect, whereas steam is always in the first effect. Okay, here both steam and feed are going to the first effect and they are going parallelly. Okay, and the sum of rates of water evaporated from the first and second effects is 1 kg per second. So what is the meaning of that? The vapor evaporated from the first effect and that from the second effect, there is a sum of the rates of water evaporated. This V1 plus V2 is adding to 1 kg per second. And the temperatures of the exit streams from the first and second effects are 160 degrees Celsius. These are all the exit streams, and this is at 100 and this also at 100. And from the second effect they are at 60 degrees Celsius, or this is at 60, this also at 60, which means solution is boiling at 60 in the second effect and 100 degrees Celsius in the first effect. And already we are given with feed is at 60 degrees Celsius. Okay, the specific heats of the aqueous suspension, always the feed solution and this solution and whatever the leaving solution are having a specific heat of 4 kilojoule per kg Kelvin. The latent heat of evaporation for a phase change, latent heat for phase change are 2200 kilojoules per kg. What is the meaning of that? The energy for evaporation per kg or energy from condensation are 2200 kilojoules per kg. So for this vapor or this steam, all are having the same latent heat, which is 2200 kilojoule per kg. So we are asked to find what is the steam economy. The steam economy is defined as the amount of vapor generated, or is total amount of evaporation per kg of steam supplied. So the total evaporation is here, it is V1 in the first effect and V2 in the second effect. So the total evaporation is V1 plus V2 and steam to the first effect is S. So this is the economy in fraction or is in kg per kg. Okay. So we have represented every data in the schematic. So what is needed is we need to find this V1 plus V2 and S. So of course V1 plus V2 is already known as 1. So we need to find simply the quantity S. So how to find that? So before that, let us see the flow rates. So feed is entering at 1.25 kg per second, and this V1 which is leaving the first effect, which is getting condensed, and this is leaving as a condensate, that is no longer available. And again feed is entering at F2, which is leaving as V2 and this product of 0.25 kg per second. So how much of otherwise say how did we find this 0.25? This is simply from this F1 is entering, which is leaving as V1 plus V2 and this product. So F1 equal to V1 plus V2 plus this product. So otherwise F1 equal to V1 plus V2 this product, or this product, if you to get this product, simply from feed, we can subtract these two quantities. So we'll be getting the product flow, which is obtained as 0.25 kg per second. So now these data are needed, that's why we are doing that. Now, so we need to find, we can write this mass balance, energy balance. Of course, mass balance doesn't have any role to play. Already we have written one such thing. And of course, we can write the energy balance. So what is the energy required for heating the feed contents, which is simply feed content to the boiling point of the solution, which is flow rate. We take it as F1 is the mass flow rate, that multiplied by specific heat, m dot Cp, or is flow rate, mass flow rate into specific heat into delta T. This is m, or is m Cp delta T, like that, no? So F is flow rate, so the F is mass flow rate. So we have this heating energy required for heating the feed. So we need to supply energy of 200 kilojoule for heating a feed of 1.25 kg per second. And this feed is at 60 degrees Celsius, that is to be raised to the boiling point of 100 degrees Celsius. So for raising the feed from 60 to 100, we need to have this much of energy. And additionally, we need to generate a vapor of the flow rate V1. So for that, what is the energy? The energy required for vaporizing that is V1 into lambda. So this is simply latent heat energy for the phase change, and this is for energy for feed, heating the feed to the boiling point. So these two quantities are to be supplied by the condensing steam entering at a flow rate of S. So mass, of course, it can be written as ms, or okay, m dot s refers to the mass flow rate of steam. Otherwise, better we'll use the same convention here. Already we have used s here, so here also it is to be in s. Sorry, what is it? This is simply s. Okay, so we need to find s, that's ultimate task. So for the first effect, we can write, so what are all known to us? We are, of course, this T1 is already available, which is the boiling point in the first effect, boiling point of the first effect, and TF is known, and V1 is not known directly. We know only this V1 plus V2. F1 is already available, so we can since we know only V1 plus V2, so using this equation we cannot do anything. We can write the energy balance for the second effect as well. For the second effect, this heating is done by this V1. So V1 into lambda is providing energy for this vaporization, as well as making the feed from the feed temperature to the boiling temperature. Of course, the feed is at a higher temperature. This feed is also entering at higher 100, and vapor is also entering at 100, whereas boiling is happening at only at 60. Otherwise, from the feed also we are going to get energy. So of course, as like for the first effect, we can also write the second effect energy balance. So V1 into lambda, that is energy given by this condensing vapor, that is equal to energy required to heat the feed from its temperature to the boiling point, plus the latent heat of energy for vaporization. So here this energy, this is T2 minus 100, that is T2 is what is the temperature of the boiling solution. So otherwise, actually we are going to get energy from this vapor itself. Of course, okay, this is going to be a negative quantity. Here we need to know F2. So F2, so what is F2? F2 is this quantity F2. Whatever is entering as F2, that is leaving as V2 and this product. So F2 is simply V2 plus 0.25. You can replace this F2. F2 is leaving as V2 and plus 0.25. So F2 is V2 plus 0.25. So otherwise now the unknown, we have this V2 here, and F2 is also written as V2 plus 0.25. So here we have everything. Here we can also replace this V2 using this condition V2 plus V1 equal to 1, that is already given. So using that, we are going to get this V1. So once V1 is available, we can go to this equation 1. So 1, and in the 1 everything is known except S now. So otherwise F1 is already given, and V1 already, V1 just we have worked out, which is 0.472, and this is 2200, here also 2200. So yes, we are getting. So as already said, we'll use this same terminology, what is called as yes. So this is yes. So what is here is simply V1 plus V2 by S, which is equal to, or is S is obtained as 0.563. How did we got that? Say simply this equation, no? The equation 1. Equation 1 is having S lambda. Already we have worked out this V1. So, and also we are given with F1. So we are getting this S. So S is coming to be 0.563 kg per second. So what is economy definition? This amount total evaporation by steam supply. So evaporation is totally 1 kg per second, and steam supply is 0.563 kg per second. So that ratio is given coming as 1.78. Otherwise the steam economy is 1.78. So that is the answer. Okay, thank you.